So we're starting on page 599, section 1 of chapter 12. We are doing Introduction to Calculus. Basically, calculus came about because pre-calculus doesn't solve all the problems, all right? Pre-calculus, I say, is a stagnant world. By that I mean you have a basic shape, rectangle. You want to know the area of a rectangle. The area of a rectangle will always be the same formula, base times height, always, right? But the world is not stagnant. Things move, all right? And so you then have something that looks more like this, and I want to find the area of that. Well, that's not a basic formula, okay? And so we have a moving world, a motion world, not a stagnant world. Not that geometry doesn't play a huge part, because in your world of geometry, you can see that buildings are created and that we can do satellites with geometry and trigonometry. However, there are some problems that cannot be solved in the pre-calculus world, which is why we look at the calculus world. And so the first thing we talk about in the calculus world are limits. The reason we talk about limits is because this is the first non-stagnant thing that we are looking at. If I were to give you a graph and I say, here is x, what is y? Then you would simply go to your x value, go up to your y value, and you would tell me what it is, right? If I said, what is the y value given x is 2? You would say, well, that's clearly 2, right? But then with limits, all of a sudden you take that away, and you're not talking about an exact point. You're talking about what is the graph moving towards as I move towards something. That is what limit is. And so if I say, what is the limit as x approaches 1, then all of a sudden I'm saying, what is the y value doing as I get really close to 1? Not necessarily what is it at 1. And so if I were to look at this graph, this is kind of a trick question because it depends on which way you're coming from. If I look at as my graph approaches 1, if I'm just tracking along here, and I say, well, what is it approaching? Everything in you would say it's approaching 0 because that's where it is. But you'll notice at 1, it actually jumps. So if I'm coming from the left-hand side, I'm going to say, well, it's approaching 0. But if I come from the right-hand side, I would say, oh, it looks like it's approaching 1. All right? And so it depends on which way you're coming from. This is my x value at 1. As I travel the graph heading towards that, starting at 0 going this way, my brain would think I'm just going to stay on 0. That's what I've been doing. But as I travel the graph this way, my brain would say, well, I'm going to stay at 1. That's what I've been doing. And so then you start looking at not stagnant world, but movement. What is the graph moving towards, even if it doesn't actually hit it? Why they gave me a step function for this particular one is odd, because in a step function, you actually don't have an overall limit, because I'm actually approaching two different things. On a step function, I would say, well, from the left-hand side, my limit is 0. From the right-hand side, my limit is 1. Overall, I don't have a limit because I'm approaching two different things. All right, and so now we are looking at what is the graph approaching, not what is the graph actually doing. And so we're going to start looking at these a little bit differently. Look at the example that they've given us here. There are a couple of things I could do. Let's say I wanted to pick 0. All right, x equals 0 right here. This is the point that I'm moving towards. All right. So as I travel on the graph from left to 0 and from right to 0, I want to figure out what my y value is doing. And so if let's say I'm on a roller coaster, y'all just went to Carowinds, I'm on this roller coaster. This is moving towards x equals 0, is it not? What am I moving towards on the y value? Right here. Negative 1.5, right? What about coming up the roller coaster, heading towards 0? What is my y value moving towards? Negative 1.5. When I hit 0, does the graph have negative 1.5 in it? There's a hole there, correct? So if I were to say f of 0, we have a problem. f of 0 causes a problem. I can actually look at the graph and tell that, can't I? I have a discontinuity there. Prior to this, it's one that you can cancel, which tells you it's going to be a hole. Yes? When I have a discontinuity that cancels, it is a hole. Correct? All right? So I know there's a hole there. So I actually know that this guy does not exist. The function at x equals 0 does not exist. It is a hole. However, the limit as x approaches 0 is a completely different question. It actually doesn't matter if the function exists there or not. It matters if it is approaching a specific number, and it is. As the x values approach 0, the y values are approaching negative 3/2 or negative 1.5. And that is your limit. Even though at that point you don't actually have a hole, the graph doesn't exist. It doesn't matter whether the graph exists or not. It matters what you are approaching. Sometimes you will approach a number that is a hole. Sometimes you will approach a number that's actually on the graph. All right? Sometimes, like this example, negative 2. Let's find negative 2. Negative 2 is actually right here. This is negative 2. Yes? What do you notice about negative 2? Well, it depends on which way I'm coming from, doesn't it? If I'm coming from this direction and approaching negative 2, what's happening to my y value? It's shooting off into negative infinity. So from the negative side, so as x approaches negative 2 from the negative side, that's how we note that, it's approaching negative infinity. All right, if I were to ride the roller coaster, it would shoot down. From the right-hand side, if I'm driving along here, and I'm approaching negative 2, what's happening to my y value on this side? Where's it going? Positive infinity. And so if I were to look at the limit as x approaches negative 2 from the right side, positive side, my graph shoots all the way up, positive infinity. All right? However, this is asking overall. Overall, these two things are not the same, are they? So overall, I have this particular answer like this. Overall, I don't have the same limit, so it doesn't exist. Here, however, let's go back to here. When I did this guy, even though at that point I have a hole, from the left-hand side and from the right-hand side, I was actually going towards the same point, which means I did have a limit. It was negative 3/2. So limit is literally saying, what is y moving towards as x moves towards the given number? I'm going to give you a number for x. You say, okay, as x is traveling towards that number, what is my y value traveling towards? Not necessarily what it is. What is it moving towards? If from two different directions they are moving towards the same number, that is your limit, all right? If they are moving towards two different numbers, that could mean you have a right limit and a left limit. But overall, if they're not heading towards the same point, you do not have an overall limit. All right? Does that make sense? This is what limit is. Limit is not the value that it actually is. It's what it's moving towards. What is it moving towards? The first way to find limit is, can you just plug it in? If the graph is continuous at that point, then you could potentially just plug in the number, and it will tell you what it's moving towards. So let's look at the first one, x squared minus 6x plus 17. What type of graph is that? It's a quadratic, which produces what picture in your head? A parabola. A parabola, just a basic parabola, is a continuous function, correct? There are no breaks in parabolas. So for a parabola, if they give me a number, I'm not going to have any discontinuities. I can literally just plug it in, because whatever number I plug in, since it's continuous, that's the number it's going to approach from both sides. So my first method to solving for limit, if I have a graph, I'm just going to literally look at the picture and say, this is what it's approaching. I can see it visually. If I'm given a function, my first process is, can I just plug it in? If I can just plug it in, it means it's continuous at that point, and we're good to go. So for this one, I'm just going to plug it in. I'm going to say, well, if I want negative 8, I'm going to plug in a negative 8 for all my x's. Negative 8 squared minus 6 times negative 8 plus 17. 129 is my limit. That is my limit. All right? Natural log function. Now, not all natural log functions are going to be continuous. We could have an actual problem with the log, right? Natural log of a negative number, you're going to have an error. It's not going to exist. But in this case, as x approaches 4, 4 does not cause a problem. So I can literally just plug it in. 5 natural log of 4 plus 3. 5 times the natural log of 7 is approximately 9.73. That is going to be my limit. Direct substitution works. Cosine. Is cosine continuous? Think about your cosine graph when we graph cosine. It is a wave, correct? It is continuous. Now, that's not true of tangent, cotangent, or any of your other ones, actually, secant or cosecant. But sine and cosine are continuous functions. So while you may have to pull back in your memory what pi over 6 is when you plug it in, it's still a continuous function. You can just do substitution here as well. So to find this limit, I'm going to plug it in. The cosine then of 2 times pi over 6. So that's the cosine of pi over 3, which hopefully you know is the cosine of a 60-degree angle, which is... Here's what I want you to gather. Given a function and it says, what's the limit as x approaches this? The very first thing you're going to try is just plug it in. Can I plug it in and does it not cause a problem? That means it's a continuous there. At least at that point, it's continuous, which means I can plug it in and I can just get the limit. If it is continuous at that point, then that is going to be the limit at that point as well. All right? So first step is see if you can plug it in. So try it. So use limits to describe the end behavior. There's a shortcut for end behavior. What is it? Shortcut. What's your shortcut for end behavior? What do you remember about end behavior? You look at two things. There's two things you look at for the end behavior of a function. The leading coefficient and the degree. Yes, degree. So if my degree, let's not write in that. So if my degree is even, they're going to go the same direction, right? If my degree is odd, they're going to go opposite directions. All right, yes? If my leading coefficient is positive, they're going to go up. But both ways, actually. If it's negative, it's going to go down. So if they're the same direction, it goes up, same direction down. Odd means they're going to go up from left to right, or negative would be down from left to right. Yes, continuously up, continuously down is what it means by up or down. So if I look at this guy, we have an odd positive, all right? Which means the function, whatever happens in between is unimportant. For this question, the function's going to do that, right? Odd is opposite direction, positive continuously up. To write that with limits is, you would say the limit then as x approaches positive infinity is going to be positive, and the limit as x approaches negative infinity is going to be negative infinity, right? That's how you write it using limits. Okay, because all you're doing is you're telling me as x approaches this, what is my y doing? Look at the other guy. He's even and negative, all right, which means pictorially, he looks like that, okay? Same direction, both down, all right? Which means if I write it in limit form, as x approaches positive infinity, what is my y doing? It's approaching negative infinity. And as x approaches negative infinity, what is my y doing? Same thing, all right? So all they're doing is pulling back from what we've already done because I actually made you give me your end behavior and limits already, all right? But that's what it's saying. Using limits to describe end behavior is literally saying as x is going towards some number theory, in this case, what is my y doing? All right, so that's all you're doing. You're just writing it in limit form. We also had a shortcut for this. All right, there was a shortcut for this too. This is what we used when we did horizontal asymptotes. Shortcut for this. What was our horizontal asymptote shortcut? Coefficients. Yeah, we do use coefficients and degrees. All right, so the first thing we look at is degrees. The next thing we look at is coefficients. All right, so my degree of my top, so degree of the top is what? 4. What's the degree of my bottom? I have an x here. I have an x here. How many x's do I have here? 2. So if I multiply those, I'm going to have x to the 1, 2, 3, 4, right? So degree over degree, which means if I look at this and move towards infinity, which is what this first guy is doing, then I am going to look at my leading coefficients here, my leading coefficients. And it actually doesn't matter if I'm going towards positive or negative infinity on this particular one because it's same degree. So what is my coefficient on the top? 2. What's my coefficient on the bottom? 1. So my limit here is 2. All right. Let's look at the next one. The next one, we have a little bit of a problem here. All right. Because I can't just plug in a -1, can I? What happens if I were just to substitute here? I would have a 0 on the bottom. This causes an issue, all right? And so I actually need to figure out what's happening as I get close to -1, we're going to look at it from both sides. So we're going to look at it as we get close to -1 from the left-hand side and from the right-hand side, okay? So the limit as x approaches -1 from the left-hand side. It's going to be something slightly smaller than -1, like -1.2, all right? So let's talk about the numerator. If I plug in any negative number into the numerator, is my numerator going to be positive or negative? Positive. All right. What about this x? Is it going to be positive or negative? If I plug in -1.1, x is negative, right? Any small negative minus 3, is that positive or negative? Negative. And something slightly smaller than -1 plus 1, but I square it. That will always be, if I square anything, it's going to be positive. This is going to move towards an infinity. I'm just trying to figure out which one. All right? Which one? Is it going to be positive or negative infinity? Positive infinity. Everybody agree with that? Does everybody see what I did there? I just took something smaller than -1 and to figure out what it is. So this guy is going to be positive infinity. We just need to figure out, is the other side positive infinity? All right? So we're going to do the same thing with the limit as x approaches -1 from the right-hand side. Something ever so larger, like -0.9. -0.9, all right? Plug it into the top and I take it to the 4th power. Anything to the 4th power is positive. Something a little tiny negative. Well, that x is going to be negative. A little tiny negative minus 3 is going to be negative. Any number squared is going to be, what is this guy moving towards? What is my overall limit? Positive infinity. So this guy is infinity. Everybody see what I did there? All right. So if it is something that's going to cause a problem and you cannot cancel it out, we're going to cancel some, then you're just going to see, okay, it's going to approach an infinity at this point if it causes a problem that I cannot cancel out. We're going to do the same thing for 3. So as x approaches 3 from the negative side, we're going to do that same process, okay? That same process. From the negative side, it means something just a little bit smaller than 3. The numerator is always going to be positive, right? Anything to the 4th power is going to be positive. Something smaller than 3, like 2.5, that's going to be positive, right? Something slightly smaller than 3 minus 3 is going to be what? Negative. And anything squared is going to be, what is this guy approaching? Yeah. You have to have an even number of negatives, right? But this is basic like pre-algebra. When you divide a negative by a negative, etc. All right, let's look at it when we approach it from the right-hand side. All right, my numerator, we decided, is always positive. That x, well, 3.5 is positive, right? Something slightly larger than 3 minus 3 is going to be positive, and anything squared is going to be positive. This guy is approaching positive infinity, right? One side I'm approaching negative, one side I'm approaching positive. So overall, we're going to say it does not exist. Everybody see? When they want you to find the limit of a sequence, then you can apply that same kind of method that you're looking towards. What is it moving towards? Sequences go on infinitely, potentially. So if I'm talking about n, I'm talking about what happens as n is going infinitely in some direction, all right? So if I'm doing an infinity limit for a sequence, I'm going to use those same shortcuts, all right? Which means for this first one, my degree on top is the same as my degree on bottom, all right? So if I'm talking about what is my sequence approaching, I'm doing this method right here. Same degree on top and bottom. What's my shortcut? Use what? Use your coefficients. So what is this guy going to be? All right. This next guy is a geometric sequence. We already did infinite geometric sequences 2 chapters ago, right? What do you look at to decide if it's converging or diverging? This guy, not only does he not converge, he actually equals a -1. So what's your sequence going to do with a -1 to a power? What's going to happen to your sequence? Think about it. To the first power, to the second power, to the third power, what's going to happen to your answers? It's going to ping pong, right? Between -1, +1, -1, +1. Everybody see that? -1 to the first power is -1. -1 to the second power is positive. Third power, negative. Fourth power, net positive, right? It's going to ping pong. It's also called oscillating, all right? Think about a fan. What does an oscillating fan do? What does an oscillating sprinkler do? It goes back and forth, right? It just pings back and forth to the same points, all right? That's what an oscillating function does, and that's what this is. It's an oscillating function. It pings back and forth. So you do not have a limit when it is an oscillating function. Why? Because it's not approaching anything. It's ping-ponging between two, all right? It actually does this zigzag motion, all right? So when you have an oscillating function like this, when you see the graph of an oscillating, it jumps like a heartbeat would, like a really fast heartbeat. Think about that on a screen, okay? Oscillating functions don't have an overall limit, and that's what this guy does. He's an oscillating function. He doesn't have an overall limit. He pings between two and just bounces back and forth. So something like this is not going to exist. An oscillating function is another one that does not exist.
Do we have to explain, like...
This actually doesn't matter that it is a negative. It is going to go back and forth, but it's not going to ping between two numbers. It's going to actually go back and forth and zigzag towards a number, okay? Anytime you have a function like this with a fraction going towards infinity, your denominator is getting larger. And so is your numerator, but when it's exponentially getting larger, your denominator is larger already and getting exponentially larger. So what do you think this guy is going to converge towards? Zero, okay? Because 3 to a power is going to grow much faster than 2 to a power. It's an exponential function. So when you have something like this guy is going to converge to 0. Your denominator is going to be growing faster because it is a larger number. And so you're going to have a really huge denominator and a rather large numerator, but the denominator is going to exponentially get larger faster. And so that is going to go back and forth because it's negative, but it's going to snake towards 0, if that makes sense. This guy, that guy's just going to continually do what? Yeah, multiply by a negative number specifically. So what am I moving towards for this one? Negative infinity, right? My n is going to increase without bound, and it's being multiplied by a negative number. So this is going to move towards negative infinity. So some of these are very logical. When it's not just a set, plug it in and give me the limit. then there are going to be times when you have to just use your logic skills, okay? And we're going to do some functions that we can actually cancel and simplify and also plug in or rationalize. For things like this, you're going to have to use either your shortcuts, or you're going to have to say, what is this function actually doing? Think of a picture in your head like we did with your oscillating function. Page 604 in your books. Couple things here. The limit of a constant is the constant, okay? So why is that? Well, we're talking about functions, all right? What does a constant function look like? Y equals 3. What does that look like? What does y equals 3 look like? It is a horizontal line, correct? So anything that you approach on a horizontal line is going to stay on that horizontal line. So if I am asking you for the limit of some constant function, the limit is the constant. Whatever the constant is, that's what it's going to stay. It's a continuous function. It's a horizontal line. It doesn't matter where you move on that horizontal line, you're going to stay on that horizontal line. Okay? So the first concept is, well, the limit of a constant is just the constant. The limit of the identity function, y equals x, that is also a constant. Your limit is just going to be what you're approaching, right? If I have the function y equals x, which is what my constant function is, and I want to know what is y doing as x approaches a number, well, it's going to be approaching the same number. It's a one-to-one slope there, right? So for a y equals x function, over 1, up 1, over 1, up 1. Whatever you're approaching on x, you're also approaching on y. They're the same number all the way up the line, all right? Scalar. Your scalar is just going to multiply your limit by whatever. Remember, a scalar is just a number that's multiplying in front of it, all right? So if I have a limit function and I have found the limit and it is being multiplied by a number, if the function is being multiplied by that number, so will the limit, all right? It's just going to increase where you are, any scalar. Sum. If I have a polynomial type function, or I'm multiplying, or adding two functions. If you add two functions and they both have definable limits, you can just add their limits. That's all these are saying. The limit of a power. So if you take a function to a power and you're doing the limit and you have an actual limit for that function, you can also take the limit to the power as well. All right? So let's look at finding limits using your properties. Look at this first example. They want me to evaluate the limit of this polynomial. We're going to write it out long. This is not how you're going to do it logically. They're just showing you the properties, okay? So here's the properties. The properties say, well, if I'm adding or subtracting it, I can find the limits individually and add and subtract it. I can do the limit as x approaches 2 of the 2x squared minus the limit as x approaches 2 of the 3x plus the limit as x approaches 2 of the 5. Now, in real life, what do you think I would probably just do here? I would just plug it in, all right? They just want to show the properties. All right, so the property here, this is a scalar, right? 2 times the limit as x squared, as x approaches 2 for x squared. I can plug it in, substitution, right? So this guy here is going to be 2 times 2 squared, also known as 8. This is a continuous function. I can use substitution. 3 times 2, that's going to be 6. And this is a constant. What's the limit of any constant? Just the constant. And so that is why I can just do substitution here. Because I have 8 minus 6 plus 5, my overall limit is 7. All right? Product. If I'm multiplying two functions, I can multiply their limits. If I'm dividing two functions, I can divide their limits. There is a caveat on the division. What is always your exception on division? There's always an exception on division. What is it? Denominator cannot equal 0. So the limit of your denominator cannot equal 0 for this to apply. So they want the limit as x approaches -3. The reason I can just do substitution here is, 1, -3 doesn't cause a problem in my denominator. 2, that is just adding and subtracting functions on the top and dividing functions from top to bottom. All right? And so the reason I can just do substitution here is nothing causes a problem. and my properties tell me I can just plug those in. All right? And so you can literally just plug it in. Not that we're going to do it all out, but they just want to show you the properties. They wrote it all out. Limit as x approaches -3 of x cubed. Limit as x approaches -3. I'm not going to write it all out. All right? You can just plug it in. If that -3 caused a problem, we would not be able to do that. It does not cause a problem. I think this is what they say it simplifies too when you do all that craziness. 19/5 then would be my limit. So what happens when it does cause a problem and it's not going to approach an infinity? So look at example 3. The first method we talked about is visually. If you're given a graph, you can look at the graph and tell me what the limit is. If you can plug it in, the next method is just use substitution and plug it in, okay? There are going to be times when you say, oh, this is an odd function, it's approaching infinity. Or there's going to be times like this. What happens when I plug in a 2? You have a 0 in the denominator, okay? So my second method that I'm actually going to start with here when I have a problem is to see if I can get rid of it, all right? This pulls back from graphing, all right? The first thing we did with graphs is we factored it to see if it is a removable or a non-removable discontinuity, yes? So is the denominator factorable? Yeah, it is, right? So my numerator is x minus 2. My denominator factors to what? Factors to that. Yes? -2, +1. Yes? So if I have this particular limit, there's something I know. At 2, I have a problem. Yes? At 2, I have a discontinuity. Specifically, what type of discontinuity? A hole. Why do you know it's a hole? Because I can cancel. So when you're finding limit, you're actually going to do that canceling. You're going to say, I'm going to cancel these guys. I'm going to rewrite him like this. Now do I have a problem with substitution? No. So now I can just use substitution. Now I could just use substitution. This is also how we found the y value of my hole. Remember when we were graphing? And you're like, how do I know where to put the hole of my graph? Right? You found the y value by canceling and plugging it in. What you were also doing was finding the limit as you approach that hole. Okay? And so your limit is what happens when you plug it in. 1 over 2 plus 1. My limit here as x approaches 2 is 1/3. So your next method is see if you can factor and cancel your problem out, then substitute. All right? Can I cancel, get rid of my problem, and then substitute? I can. This is my limit then. So if I were to draw that graph from left and right, I would be approaching 1/3. At that particular number, there would be a hole. But going towards 2 from the left and towards 2 from the right, my graph would be approaching 1/3. Even though at 1/3, I would see a hole there. My limit would still be 1/3. I cannot substitute, correct? Second problem is I cannot factor. Well, I mean, I can factor the denominator a little bit, but that doesn't help me, okay? Does that make sense? So factoring doesn't help me. I still have a problem if I factor, all right? So anytime you see a radical, either your denominator or numerator with a radical, your standard method of getting rid of it is typically to rationalize, all right? Rationalize. And so what you'll find when you rationalize is that typically gets rid of your problem. Now, don't let it scare you because I actually leave it alone. I don't foil the non-parts that I'm rationalizing. So for example, if my root is on the top, I am going to rationalize the top. How do I rationalize a radical out of my problem. What do I multiply by? It's the same thing I did with imaginary numbers. I multiply top and bottom by what? Conjugates look like this. If this is my original polynomial or binomial rather, the conjugate is this guy, okay? Because what happens when I multiply conjugates is what I just factored in my problem, right? It factored to x plus 1, x minus 1. You get the difference of two squares when you multiply conjugates, always, okay? So what that does to this guy is it gets rid of my radical in the numerator, and it's actually going to help me get rid of my problem in the denominator. So what I'm going to do is I'm going to take this guy and I'm going to multiply the top and bottom by the conjugate, which means I leave the two terms exactly the same, but instead of a minus, I'm going to do a plus. And I'm going to do the same thing on the bottom. All right? The only one I have to actually simplify is the one that is the conjugates. The other one you can kind of leave alone. It's going to take care of itself. All right? So when I multiply conjugates, remember, when I multiply conjugates, I always get the first guy squared minus the second guy squared. Always. That's how conjugates work. So in the numerator, the first one's squared. What happens when I square a square root? It cancels the root. So I just have the x plus 3. It's always going to be minus. And then I have another root. What happens when I square that square root of 3? It cancels that guy. In the denominator, I'm going to go ahead and factor this. What does that factoring look like? Well, I take an x out, and I have x minus 1, and then I'm multiplying by this huge guy right here. Just write him the way he is. Don't do anything with him. Don't try to FOIL. Trust me on this. All right? Yes? My numerator simplifies. What is x plus 3 minus 3? It's not a trick question. It's just x. So this whole thing just equals x. Now what can I do? Now I can actually use my canceling method, can I not? I can reduce that top x with that bottom x. What do I have left on top? 1. Please don't forget that you have a 1 on top. It's going to change your limit. So now I have 1 over this big, huge thing, x minus 1. And then this crazy thing here, square root of x plus 3 plus the square root of 3. Don't forget what you're doing. You are saying the limit as x approaches 0. Can I plug in a 0 now? Yeah. Actually, plugging in a 0 doesn't cause a problem anymore. Now I can do substitution. I got rid of my problem. So in the numerator, I have a 1. Here I have 0 minus 1. What is 0 minus 1? Negative 1. I have 0 plus 3. That's just the square root of 3 plus the square root of 3. Yes? So I'm going to pull this negative out. Negative 1 over, what's the square root of 3 plus the square root of 3? It's 2 square root of 3. Now, they actually left it like this. You can rationalize your denominator if you want to. If you were taking a standardized test, make sure you understand they could do it like this, or what's another way they could possibly write this answer? What's another way to write this answer? Yeah, so rationalize it. Square root of 3 over 6. Right, rationalize. So those answers would be the same, okay? What's my problem? If I just plug in a pi, what is the sign of pi? Y value at pi over here. It is 0, right? It's on my x-axis, yes? That causes a problem. However, 1 minus cosine squared. There's some pretty repetitive identities that we used over and over and over and over called the Pythagorean identities. The most famous of the Pythagorean identities looks like this. Yeah, there we go. So what is 1 minus cosine squared of theta or x? Sine squared. Okay, so just like you could factor out a problem, you can use a trig identity to get rid of a problem. So I could rewrite this guy as this, sine squared of x over sine of x. What do you think I can do? I can cancel my problem, can I not? So this is the same thing of this, which is that. That is my limit. Okay? So we're not going to pull some random, very hidden trig identities, but you will need to remember ones that you use so often that you probably can still say them, like something like this. Sine squared plus cosine squared equals 1, right? And you can cancel out your problem when you have something like that. Anytime you see an infinity, the first thing you're going to check is, can I use one of my shortcuts? Okay, and so we talked about this a little bit in section 1, but remember your shortcuts. If your degrees are the same, you're going to use your coefficients, right? If your degree in the denominator is larger than your degree in the numerator, then your limit is going to be 0. All right? And if the numerator is larger than the denominator, you're likely approaching either positive or negative infinity. You need to use your logic skills to figure out which one. All right? Meaning, go from the left and the right and see if you're approaching positive or negative infinity, and if they're approaching the same thing, that is your limit. Okay? Just like we did with 3 and 1 on that other example. In this case, however, this is a really easy limit. Why? My degrees are the same. I don't even have to worry about anything else. All of the rest of that stuff will cancel itself out because it's like adding 1 to $1 million. You're not going to notice it. You're really going to notice those leading coefficients. That's why we look at those. So in this case, if I'm approaching a limit, my shortcut says ignore everything except those leading coefficients because my degrees are the same. So this overall limit is going to be 6 over 2. Obviously, I'm not going to leave it like that. My overall limit looks like that. All right, those are simple.